Okay, welcome to Let's Get to the Marks. We're looking at AQA A-Level Chemistry, Paper 3, Friday the 23rd, 2023. I found this paper on the PMT website. You can get it on the AQA website as well. The code for it is 7405/3. Let's get into it. Section A, question 1. Ethyl ethanoate can be made by reacting ethanol with ethanoic acid in the presence of concentrated sulfuric acid. So here you can see we've got the skeletal formula for ethanol. It's reacting with ethanoic acid, skeletal formula as well, reversible reaction, and we're making ethyl ethanoate. And of course, this is a condensation reaction. We are releasing a molecule of water. Here we have the method. A mixture of ethanol, ethanoic acid, and concentrated sulfuric acid with anti-bumping granules is heated under reflux for 10 minutes. The apparatus is rearranged for distillation. The mixture is heated to collect the liquid that distills between 70 and 85 degrees. The distillate is placed in a separating funnel. The aqueous sodium carbonate is added and a stopper is placed in the funnel. The mixture is shaken, releasing pressure as necessary. The lower aqueous layer is removed and the upper organic layer is placed in a small conical flask. Part 6, anhydrous calcium chloride is added to the sample in the conical flask. The flask is shaken well and left for a few minutes. 7, the liquid from the flask is redistilled and the distillate is collected between 74 and 79 degrees. Woo, that was serious. 1.1, state the role of the concentrated sulfuric acid in the reaction, 1 mark. So we can see here we used concentrated sulfuric acid in step 1. Also in the mixture was the ethanol and ethanoic acid. So if we come up here and look at this, ethanol's a reactant, ethanoic acid's a reactant. They've combined. There's nothing here that the sulfuric acid you can see has directly influenced on that. The sulfuric acid, of course, is acting as a catalyst, lowering the activation energy. So catalyst, that is the role of the sulfuric acid. You could say lowering the activation energy as well. All right, let's move down to 1.2. 1.2, the reaction mixture is flammable. So ethanol, alcohols, flammable fuel, suggest how the reaction mixture could be heated in step 1. We don't want the ethanol, which is going to be quite volatile, have quite a low flammability point or whatever it's called. It's going to catch a light quite easily. So the apparatus, how are we going to heat it? Obviously not with a naked flame, with a Bunsen burner. That's going to cause the ethanol to catch a light. So if you don't want a Bunsen burner, what are you going to use to heat more gently or without chance of your reactants catching a light? And of course, we're going to use like an electric heater here. So I'd just use like an electric heater, no naked flame, e.g. Bunsen burner. So let's not expose it to a naked flame. Let's not have a big fire in the lab. That sounds like a good idea. Okay, bosh. 1.3. Let's shrink that down a little. And again, so we can actually see what's going on here. 1.3, figure 1, that's this figure here, shows how a student set up the apparatus for reflux in step 1. So this is the reflux where we've got the ethanol, ethanoic acid, we've got the catalyst, the concentrated sulfuric acid, we've got anti-bumping granules in there as well. You should assume the apparatus is clamped correctly. So we've got clamps on here. Identify 2 mistakes the student made in setting up the apparatus. State the problem caused by each mistake. So we're heating it up here. We've got this bung in the top here. And the problem with this, it's sealed tight. There is no area to release pressure. And so you could get an explosion. So mistake 1, the reaction vessel is completely sealed. So pressure, well, that's the mistake. And the problem is pressure build-up could explode. I'm not talking about like bomb explosion, but yeah, you could have the lid fly out and your contents go everywhere. So that's going to get us 2 marks. It did say there's 2 mistakes and we need to say the 2 problems. So I'm going to scroll down for the next one. So we've got a second mistake and the problem caused. So what the problem is here, yikes. This can be confusing sometimes. The water is coming in here. Sometimes that's not a bad bet. It's away from the heat source, but The water's coming in here and traveling down here. Generally, you want the water to come in from the bottom on all condensers. You want the water to come in from the lower point and push up to the higher point. The idea is if the water comes in here, it will completely fill the condenser. And what you'll get there is an efficient transfer of heat energy from the vapor to the water. And that means that you're going to get a more efficient heat transfer. Your vapor is going to condense better, basically. So, but the thing that's always on the mark scheme is that if the water is at the lower point, if the water enters at the bottom and leaves at the top, you will completely fill the condenser. And that's always on the mark scheme. Sometimes countercurrent flow is mentioned on the mark scheme, but that is where you want your vapor going in the opposite direction to the water, essentially. So that we're not going to look at that for this one. We're going to say mistake, um, mistake, water enters from above. It should enter from below. So you want the water to come in at the bottom on these. It doesn't matter whether it's horizontal or vertical. The water should always enter from the low point. And the problem caused here is the water will not completely fill the condenser. So it won't fill the condenser completely. So heat transfer will not be as efficient. Groovy. That's quite common on these questions on practical apparatus. Okay, let's sing down. Right, we've got 1.4. State why sodium carbonate is added to the distillate in step 4. Explain why there is a buildup of pressure in the separating funnel, and that's worth 2 marks. So what you've got to ask yourself here is, what do you know fundamentally about sodium carbonate? What type of compound is that? Well, sodium carbonate is a base. Back in old school GCSE content knowledge, you should know that. And what a base is good for? They're good for neutralizing acid. And what acid do we have here? Well, if we have more ethanoic acid than ethanol, we're going to have excess. It's a one-to-one reaction, but if we have slightly more moles of ethanoic acid in our reaction mixture, we're going to end up with excess ethanoic acid. So this sodium carbonate can get rid of it. We can also use the sodium carbonate to get rid of the sulfuric acid. So the idea here is to neutralize either sulfuric acid, that was our catalyst, or ethanoic acid excess. So we might have ethanoic acid in excess. We want it to neutralize. Now, why would this cause a buildup of pressure in the separating funnel? Think about carbonates. So you should all know, for example, if I have sodium carbonate, oh my days, if I have sodium carbonate, let's go plus sulfuric acid. I could have written ethanoic acid here. Then what are we going to make? We're going to, oh my gosh, I can't even spell carbonate. Put a B there. Right, we're going to make sodium sulfate. And of course, we're going to make water, as you do with all these neutralization reactions, and we're going to make carbon dioxide. And what do we know about carbon dioxide? It's a gas. So you might remember all of that from GCSE. So we want to say CO2 released is a gas, will increase pressure. Cool. Lovely jubbly. So the main thing is that CO2 is a gas and we're using the sodium carbonate to neutralize excess acid. So those are your 2 main marks. I've put a bit of extra whiffle waffle there. Right, 1.5. Give a reason why 2 layers form in the separating funnel. Cool. Give a reason why 2 layers form in the separating funnel. Suggest why ethyl ethanoate forms the top layer. Right. Well, we get 2 layers forming. Look, we've neutralized. We've got water present now. Remember, it's a condensation reaction and we've got water. Remember, we've also had water produced with the sodium carbonate, removing the excess acid. So we've got water there. So the reason is ethyl ethanoate is not fully, I can't spell this next word, miscible with water. So it doesn't fully mix with water. Okay. So we get 2 layers and why would ethyl ethanoate go on top of the water? So ethyl ethanoate is less dense, is the less dense layer. So you normally get layers formed when one substance is less dense than another, then it's going to float on top. So ethyl ethanoate is going to be less dense. That would be our suggestione. Right. Next question, 1.6, state why anhydrous, the clues there, right there in that name, isn't it? State why anhydrous, what does anhydrous mean? It means without water. So state why anhydrous calcium chloride is added. If it's anhydrous, it can become hydrated calcium chloride. Why would we add something that's anhydrous? To absorb water. It is a drying agent. So what that means, it can remove all of the water. It will clump together, it will soak up the water and become hydrated calcium chloride. So it's a drying agent. So great if we're purifying this and we want to remove the water, add some calcium chloride. It's one of those typical drying agents that will remove the water. Super duper duper. Let's zing. I think this question's nearly done. What we got left? Oh, we got an amount of substance question. Right, 1.7. A student uses the method to prepare some ethyl ethanoate. So again, we've got ethanol, ethanoic acid, ethyl ethanoate, water. The student adds 10 centimeter cubed of ethanol, MR46. So as soon as I read through this question, I'm thinking to myself, these guys just mentioned MR. It's the weirdest looking triangle I've ever made. It's like a witch's hat. Right. I'm immediately thinking mass over MR times moles. The student adds 10 centimeter cubed of ethanol. We got the MR is 46 to 5.2 grams of ethanoic acid. So I'm going to group my data together to make it easy. You can do this. Some people like this. So I've got 10 centimeter cubed ethanol. And I know the MR is 46. So that's my data for the ethanol. And then they're giving me data for the ethanoic acid. So I've got 5.25 G of ethanoic acid. Let's not have the pain of watching me write that out. So let's type that out. So I've got 5.2 fam grade ethanoic acid, and that has an MR of 60. And then our product that's produced, we obtain 5.47 grams of ethyl ethanoate. And yeah, so we're going to get 5.4, hold on my days, 47 grams ethyl ethanoate. This is our product, and that's got an MR, yikes, of 88. So what do we want to do here? Oh, we're also told the density of the ethanol. So let's whack that in over here. Density ethanol. So I'm grouping all my data together. Some people, this is just a technique. I don't often do this, but this is something that some of you might find useful. Just to group your data together so you know what you're working out. So I now got the density of the ethanol. Determine the limiting reagent. So which of the two reactants are limiting? So first of all, that's going to pick us up some marks. So I'm just going to circle my reactants are the ethanol and the ethanoic acid. So that's this data here is one of my reagents and this data here. And then calculate the yield of ethyl ethanoate. Now, if I zing over here, you can see this is my product, the ethyl ethanoate. So that's that data. So first of all, let's calculate the moles of each of these and then see which one we don't have enough moles of. That's going to be the limiting reagent. You might say to yourself, I need to know the coefficient and the reaction. We can see from this, it's a 1-to-1 reaction, right? There's 1 mole of ethanol reacts with 1 mole of ethanoic acid. We can see it from that equation they've given us. So we know the ratio is 1-to-1. Let's work out the moles of each. So I'm going to start here with the ethanol. We have 10 centimeter cubed and an MR of 46. I can't quite use this. I don't have the data to use N over C times V because I don't have the concentration of that ethanol, but I do have the density. So if we know the density equation, D equals M over V, you need this in a lot of chemistry. I need the mass, because then I can use it with the MR of the ethanol. So I'm going to do density, which is 0.790, 0.790, and I'm going to multiply that by 10, which is the volume. So I've got D times V, we've arranged that, and that's going to equal my mass. And our mass is going to be 7.9 grams or 7.90 grams. So we've just found out how many grams we've got, and potentially that has garnered us our first mark. Now I need to use that and the MR, mass over MR. So I'm going to divide that by 46, and this is going to give me my moles of ethanol, and it's 0.172. So I've got my lovely moles of ethanol right there. The next stage, what I need to do is work out my moles of the other reactant, and then the first thing we can do is note down the limiting reagent. So my other reactant is really easy. I've got 5.25 and 60. So let's do, so this was for ethanol. Always good to keep up and make sure you know what you're doing there. Now for ethanoic acid, I want to do, what was it, 5.25 G, divide that by 60. Let's whack that in the calculator, and that gives us 0.0875 moles. So you tell me, what's bigger, 0.172 or 0.0875? Hopefully you realize that 0.0875 is smaller. So my limiting reagent is ethanoic acid. I'm going to be left with a certain moles of ethanol left over. Now, if I wanted to find out how many moles of ethanol I've got left over, I could do 0.172 minus 0.0875. And I'm going to find out exactly how many moles of ethanol we've got left over, but we don't need to find out how much ethanol is in excess. That's not part of the question. The next part of the question is to calculate the percentage yield of ethyl ethanoate. So I know that the maximum amount of ethyl ethanoate I can make is limited by the amount of this. It's a 1-to-1-to-1 reaction. So if I've only got 0.0875 of ethanoic acid, then I can only make 0.0875 of ethyl ethanoate. I can't make 0.172 because I don't have enough ethanoic acid. So let's find out how much ethyl ethanoate we would actually make. And I can come here and I can do that by taking the MR of ethyl ethanoate, which is 88, and I can multiply that by the moles, N, 0.0875, and that will give me the mass. So let's see what the maximum, can't spell, maximum mass of ethyl ethanoate. Oh my gosh, it's all in caps. Let's get rid of that. Maximum mass of ethyl ethanoate produced, or maximum mass of ethyl ethanoate, it's going to be 0.0875 moles times 88. What does that equal? Smash that in the calculator. Oh my gosh, where's my calculator? So 0.0875, oh geez Louise, 0.0875 times 88. So maximum ethyl ethanoate is 7.7 grams. Now, hopefully you know your yield calculation. Yield equals actual divided by maximum times 100. So let's do that. So we want to do that actual over maximum. So the actual mass we made was 5.47. So let's do that. So we're going to go 5.47. That's our actual mass of ethyl ethanoate produced. It's set it up here. You obtain 5.47. Divide that by our maximal mass, 7.7. We want to times that by 100. And I believe that's going to be about 70%. So let's go that 5.47 divided by answer equals that times 100 equals 71%. 71.03, whatever. I'm leaving it at 71%, and that is our percentage yield. Nice. Awesome. So a lot of marks on display here, 5 marks. Probably get 1 mark for the density calculation, 1 mark for working out the moles of ethanoic acid and saying that that's the limiting reactant by comparing it to the 0.172. 1 mark for working out the maximum mass, so that we're up to 4, and then 1 mark for the yield, and that's going to be 5. Okay. Okay, the final question here is suggest a reason why the percentage yield is not 100%. So why is our percentage yield, why is it not made 100%? So what you've got to do is look back up here at what we're using. So why is our yield not 100%? What do you know? And this is just some of your content knowledge about ethyl ethanoate. What type of molecule, what family is ethyl ethanoate? Hopefully, you know, ethyl ethanoate is an ester. Do you remember the three bits of like kind of knowledge about the uses of esters you've got to know? So you've got to know that esters are good in the food industry because they've got nice smells. They're good in perfume. And why are they good in all those things? Because they're quite volatile and they evaporate easily, which means like they're great for perfumes and great for like flavoring sweets and things like that and adding smells to things. Ethyl ethanoate, I think, is the one that smells like pear drops, maybe, or maybe that's a different ester. But yeah. So one of the things I would suspect is we've probably made close to the actual yield, but if we left it around for a few minutes, all the time we're leaving that product there, that ester, it is evaporating and our mass of product is decreasing. So ethyl ethanoate is volatile, so is evaporating. So product lost through evaporation. You get that with some of these organic solvents. So there we go. It can be a good thing in certain situations in chemistry. Okay. AQA Chemistry A Level Paper 3. Pentan 2-ol has the molecular formula C5H12O. Draw the display formula of an unbranched position isomer of pentan 2-ol that can be dehydrated to form a single alkene. So we need an unbranched. So we need to follow the instructions here. Let's zing out that unbranched chain. Make sure you pause the video, have a go on a scrap bit of paper, or in your head, just try and work it out before unpausing and watching me explain it. So that accounts for the unbranched position isomer. Now, they were saying that the OH was on the second carbon. We could move it to the third or the first carbon. They're the only two positions. You can have pentan 2-ol, pentanol, or pentan 1-ol, and pentan 3-ol. They're the only unbranched ones you have. So you've only got two choices, pentan 1-ol, pentan 3-ol. In this case, it's going to be pentan 1-ol, because if we do pentan 1-ol, we can dehydrate this to form one type of alkene only. There's only one alkene that can be formed from this, and that is pentene, pent-1-ene. So you can't make pent-2-ene, pent-3-ene from this molecule. So this is the correct answer. Okay, let's move on. Now we've got question 2.2. Draw a skeletal formula. Cool. Right, question 2.2. Draw the skeletal formula of a chain isomer. So now we're told we have to disrupt the chain. So we can't keep it as pentan. We're changing the chain. So it's going to be like methyl butanol or something like that. So draw the skeletal formula of a chain isomer of pentan 2-ol that can be dehydrated to form a mixture of different alkenes. So it can form more than one alkene. And what we're looking at here, peeps, we're going to want something along the lines. Now it says skeletal, but I'm doing the display just to help with the explanation. So if I just draw like, now we know we need to change the position. So for example, if I put a methyl group here, this is now butanol, right? This is 2-methyl, or 3-methyl butan 2-ol, whatever. So that is basically, we are able to form two different alkenes here. As long as the carbon atom, you see this carbon atom here and this carbon atom here, as long as they possess a hydrogen that is then going to, because what happens when you dehydrate an alcohol is the carbon adjacent to the carbon with the hydroxide group donates its pair of electrons from a hydrogen to the double bond. So here we'd be able to form like 3 mether butane, butene, sorry, 3 mether butene, or we could form um what would the other option be? 3 mether butane 2-ene. So this one here can form two different alkenes. So that is our chain isomer. I've changed the size of the chain. That can do that. Of course, there's a hydrogen atom there. So we want to draw this out in a skeletal formula. So it's a couple of ways you could draw this in a skeletal formula. So da, da, da. Oh, I could have done a methyl group there. Doesn't matter. Whatever, I'll put my methyl group there. So there you go. Um, that's what they're looking for, a skeletal formula. I could swap the OH group and have the OH group there and the methyl group there. It doesn't really matter. Um, same molecule. So this can form two different alkenes. Okay, let's look at 2.3. Draw the structure of an unbranched, a lot of isomerism here, gets my head spinning. Draw the structure of an unbranched functional group isomer of pentan 2-ol. Right. So what you need to know for this one is we need to know that you need to keep checking back to the molecular formula with isomers just to make sure that it's C5H12O. So what you might try, you might say, okay, I need to do an unbranched. What does that tell you? That tells you that we have 5 carbons, that we're going on a 5-carbon trip. Unbranched functional group. It's a straight chain. We can't have any methyl or ethyl groups coming off. So that's what that tells me. And then you might start playing around and going, what about pentan 3 own? But once you start counting up the hydrogens, you go 5, 6, 7, 8, 9, 10. You're like, oh, I'm too short. And then you might say to yourself, all right, what about if I do an aldehyde? That's going to get me more hydrogen atoms potentially. So if we zing over here and we do like pentanal like that, what do we reckon there? So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, we're short again. And after a while of playing around with this, hopefully you might be able to come up with, you don't necessarily have to know how to name it, as long as you can come up with a molecule that's unbranched with that formula. Don't worry about naming the molecule. Okay, and what we can do here is we can just put an oxygen atom in the middle, because of course oxygen can have 2 bonds, so this can go in the middle of the carbon chain, and we can have that ethyl group and a propyl group either side of that oxygen. So yeah, super duper duper. Now you could draw that as a skeletal formula, or you could draw that as a structural formula. If you're going to do like I have as a displayed formula, you need to make sure you put the H's in. I'm just being lazy and not putting the hydrogens around the outside. But there you go. That's going to get you a mark and get you that point. Quite a difficult question, but I recommend just having that molecular formula up there is what allowed me to work it out. Okay, so now we go 2.4. Another isomer of pentan 2-ol is an alcohol that is not dehydrated when heated with concentrated sulfuric acid. So this is one that will not undergo that mechanism of dehydration. Draw the structure of this isomer. So we're looking at a molecule that cannot form an alkene, even though it has a hydroxide group. So pause the video, have a go. All right, I'll go through what the answer is here. And again, I'm drawing the old displayed formula, but you know, it doesn't have to be a displayed formula. A lot of people prefer not to. So what we're going for here, we might go for like 2,2. This is the second carbon in the chain down here. I'm going to go 2,2 dimethyl. So I'm having 2 methyl groups coming off the second carbon. And then we need one more carbon atom, don't we? Because 5 carbons in pentanol. And there we go. So you might say to yourself, hold on a minute, how come that can't form an alkene? But remember what happens with alkenes. Remember, what we need is the carbon atom adjacent to the carbon the hydroxide group's on has to have a hydrogen. So ideally, if you want to form an alkene, then, oh God, this is pretty terrible going. Right. This carbon atom is the important one to know whether your alcohol can form an alkene, not the carbon atom, the hydroxide. So not this one that the hydroxide's coming off, but this one, because this would normally have an H that will slap down and donate that pair of electrons to the bond there to form the double bond. But what we find with this dimether is that there are no hydrogens on that adjacent carbon atom that's attached to the carbon with the hydroxide. And so that means that there isn't a hydrogen atom to snap off on this carbon atom and form a double bond there. So yes, this cannot be dehydrated to form an alkene, even though at first we might look at these two H's here and say, hey, aren't they going to do it? No, they're not the ones that do that. It's the H on the carbon atom adjacent to the carbon with the hydroxide group. So this carbon atom here. Okay, let's move on to the next part. Oh my gosh, what am I doing there? All over the chip shop. Right. Oh my days. Scroll down, Tom. Okay, so what we got going on here? We got question 2.5. An incomplete mechanism for the dehydration of a compound is shown. Complete the mechanism for this reaction by drawing two curly arrows on the intermediate. Name the mechanism for this reaction. So we can see here there's a lone pair of electrons going to the hydrogen there. All we got to do is come over here, and you might be like, how the hell am I going to work this out? Look at the finished product. What's happened? Have a look. There's a single bond here. Have a look at the finished product. Double bond. Where's that double bond come from? Hello. There was a hydrogen atom there, wasn't there? So what do you think has gone on there? Well, just like we have been doing in the previous talking about dehydration, we obviously have a curly arrow coming from this hydrogen. This hydrogen is going to leave the situation and it's going to donate its pair of electrons to form that double bond. So you should have been able to work that out from this. But also, what's going on here? We've got this oxygen with two hydrogens, an oxonium ion. So we've got this situation going on. We've got this plus charge here, and we got this bond here. So we need to really resolve this issue. And the way we're going to do that is the bond here is going to put its electrons here to get rid of that plus, and we're going to have the elimination of water. So we got this situation going on. Those are our two curly arrows, and we can tell that's what's happened because look over here. Where's the OH2 gone? It's disappeared. So we've had a water molecule vacate the situation, and we've had a hydrogen atom or ion vacate because it's no longer a hydrogen atom. It's donated its electrons to form the double bond. So that is going to pick you up a couple of marks for the two curly arrows. And then the name of the mechanism, this is some sort of elimination reaction. They'll probably ignore whatever else you put in front of the word elimination. You'll probably get the mark. So just it's elimination because we're losing that water molecule. Superbulous. Obviously, we can't really say we're losing a water molecule and a hydrogen ion because look, we started by the addition of a hydrogen ion. All right, so can't really say we're losing water and a hydrogen. Overall, there's just a loss of a water molecule. Anywho, that is 3 marks. Let's move on. Let's go down to 2.6 and the final part of this question on isomers and the dehydration of alcohols. So an isomer of the final product can form in the reaction in question 2.5. Draw the structure of the isomer. Oops, I need to have a look at that final product. What does it look like? So we can have an isomer of this bad boy. So, okay. So we could have, we've got this. So we could have the double bond. If you look here, the double bond could have formed here. And oh God, this is looking really messy. But the double bond could form there or there. It actually formed over here, but it could have formed here as well. Well, this CH3, one of its hydrogens could have broken off to leave CH2. So all we need to do is redraw this molecule here, but with a CH2 there and change the position of the double bond to here. So let's give that a little go. And obviously we want to leave that H because that H hasn't vacated in this situation. So let's draw that. Oh gosh, not doing a good job here, right, peeps? We're going to draw the same thing out. So C6H5. We're going to go to double bond N O. Not looking good. C. I'm going to draw this a bit to the side. CH2. So what's happened here is one of the hydrogens from the CH3 there has donated its electron here to form the double bond here, which means that this would still be like that and would still have a hydrogen there. So that hydrogen hasn't broken off. The hydrogen from the CH3 has been sacrificed to form the double bond. And that should be the molecule we are actually looking for. So lovely jubbly. Bit squished up there because I tried to fit it in with that question so I could talk about it at the same time. Hopefully you understand that. If there's anything you didn't understand about that question, just pop a little something in the comments and maybe I can get back to you as soon as possible with a reply. Question 3. Endomorphin 2 is a peptide with the amino acid sequence shown. TYR, PRO, PHE, PHE, NH2. Each amino acid is represented by a 3-letter abbreviation. TYR is tyrosine, PRO is proline, PHE is phenylalanine. Figure 2 shows part of the structure of endomorphin 2, showing the TYR, PRO, PHE part of the molecule. So we now know that this bit here, where's my pen? There it is. All right, we know that this bit here shows us TYR, PRO, and PHE. That's what is shown by all of this section that we've got here in figure 2. Cool. Now, let me just zing down so I can read the rest of the question. So 3.1, the NH2 at the end of the amino acid sequence of endomorphin 2 shows that the terminal functional group is an amide, not an acid. Complete the structure of endomorphin 2 in figure 2. So we just need to complete the end. So just in case you're wondering what the hell we got to do, they're saying they've shown us this. So that is what this is. They're saying, look, we've just shown you this, and they're asking us to complete it. So we need to add a PHE NH2 on the end, right? We need to add another phenylalanine and then a terminal group, which is NH2. We need to add that on the end. So we kind of got to look at this structure and work out what phenylalanine is. And because PHE is the last part of this 3 amino acid structure, we can just find the final amino acid in the structure and then repeat it to make the next PHE. So if you find here, look, there's an amine group right there. Okay, that's an amine group. That must be the start of the final amino acid. And there's the carboxylic group. Remember, they have an amine at the start and an acid at the end, or you could have an acid at the start and an amine at the end, but this one starts with an amine, ends with an acid. This here is the R group, this whole section here. So let's redraw that. And all we need to do is put an N, an H, and we're just redrawing exactly what we've got going on here. We're just copying what they've already done. And excuse my D grade GCSE art skills. There's the benzene ring. What else have we got to do? I've got to come back down here, draw that. We need the carboxylic acid group. That's supposed to be an H. I don't know what that looks like. Right, we're almost done. Now, that is the PHE. We've just done a repeat of this amino acid here. So we've definitely done the PHE. We've now got TYR, PRO, PHE, PHE. We just need to do a terminal, which is NH2. Okay, and how did we know that? Well, they put it up there, PHE, NH2. That's the terminal group. And it also told us that the terminal functional group is an amide, not an acid. If it was an acid, this would be OH, but they told us it's an amide. Remember, an amide has the C-double-O bond and connected to a nitrogen atom with a hydrogen like an amine, and that becomes the amide group. This whole bit here is the amide group. So they told us that that's correct. Awesome. So you're going to get 1 mark, I guess, for the terminals. It's 2 marks and 1 mark for the PHE. Right, let's move on to the next question. It says, use the structure of figure 2 to draw the skeletal formula of proline. So again, we can do the same thing. We just got to work out what proline is. Now we know we've got TYR, PRO, PHE. So we already worked out what PHE is, so I can just circle that. That was the PHE. So we don't want to draw that. And now we need to just get rid of the TYR, which is the first structure. So TYR, we've got NH2. TYR is over here. This is its R group. Now, how do I know to get rid of this? There's an amine and there's a carboxylic acid. Remember, each amino acid begins or starts with an amine or ends with an amine and then has a carboxylic acid at the other end. So that there is going to be TYR. Okay, and that means if I circle it in blue, if you can just about make that out, that means that this here is the PRO. So what do we have there? We just need to draw the amino acid PRO. Now, bearing in mind, this is once it's had a peptide bond, that there is once they form that peptide link in the amino acids. They don't want us to draw that. They want us to draw the skeletal formula of proline. So when it's actually fully connected. So we need to add 2 H's there. And what do we need to add on the carboxylic group there? We need to add an OH, okay, because it's going to be returned back to its original structure. And do they want the skeletal structure? No, we don't have to do to draw the skeletal, we have to do skeletal. Okay, cool. Let's do that now. And just add the water molecule back in, right? So we're just going to copy that and add a water molecule back in. So there's my nitrogen. I'm going to add our hydrogen back in. Remember, we only want to add a water molecule back in because obviously it was removed in a condensation reaction. And so now I'm just smash on OH. And there we go. That is, maybe I need to draw the little bond in between there. And there we go. That's what we need to do. So look, I've added the OH back and I've added an H back here. And there we go. You might say to yourself, sir, but shouldn't we have 2 H's there? We can't really because it's part of this ring structure here. So nitrogen doesn't like 4 bonds. It will then, I suppose you'll probably get the mark if you put an H there and a plus sign. But then you need to take, you only need to add 1 hydrogen. So we can probably actually, hold on 1 secondo. We can probably do this, which is basically doing the zwitterion. So we can add the plus there, but then I'm going to need to get rid of that hydrogen and put a minus there. So that will get you the marks as well. But just bear in mind that you're still just adding 2 H's and an O, a water molecule back. So best bet for me is to whack that back and whack that there and go back to that. Okay, enough waffle. Let's zing to the next question. Okay, here we go. A student hydrolyzes a sample of endomorphin 2 to break it down into its constituent amino acids. The student analyzes the resulting mixture by thin layer chromatography, that's TLC, state a reagent and the conditions needed for the hydrolysis. So there's a number of ways you can break up a protein. If you're a biologist, you can say to use like some form of protease, the enzyme that will hydrolyze those peptide bonds. But as a chemist, we're just going to go with hydrochloric acid and we need to warm it or heat it. So warm it. Okay, so we're going to need to heat with hydrochloric acid. 3.4, figure 3 shows the apparatus used for the TLC. We've got a beaker, we've got a volatile organic solvent, we've got a TLC plate coated with silica, and we've got a mixture on the TLC plate. There is a piece of the apparatus missing from figure 3. The omission will result in an inaccurate chromatogram. Identify the missing piece of the apparatus. State and explain why this piece of the apparatus is needed. the kind of clue here that should trigger you into realizing what's missing. Well, there's two clues. Number one, you may spot immediately, should there be a lid on top? You'd be right. The thing that might trigger you into realizing there should be a lid on top is the volatile organic solvent. The word volatile means it's going to evaporate easily, and the solvent is going to escape without a lid. If you keep a lid, then the atmosphere will be saturated with the organic solvent, even when it's evaporating, and it will prevent it from fully evaporating. Once the atmosphere is saturated, no more organic solvent will evaporate. So what we need to do is say the missing piece of equipment is a lid. Explanation: volatile organic solvent prevent evaporation and loss of volatile organic solvent. Why is that important? What's the issue with that? So we've just said what the problem is. Well, what's the effect? If we don't have a lid and the organic solvent escapes, what's the effect? This will prevent the mixture moving up the plate. Or we could say it will cause the plate to dry out. So if the plate gets dry, then the mixture is no longer going to move up the plate, and we're not going to get a proper distance for the solvent front, or we're not going to be able to calculate the RF value accurately. Okay, so there we go. Let's put those marks in. One for the lid, one for the lid prevents the evaporation or loss of the volatile organic solvent. I mean, it doesn't really stop evaporation. The organic solvent is going to evaporate, but once it's saturated the atmosphere, you're going to reach an equilibrium where no more solvent evaporates, and that's what the lid will create. And then that will prevent the plate from drying out. 3.5, state why the amino acids separate on the TLC plate. So why is it that proline, tyrosine, and phenylalanine, why do they actually separate? And it's to do with the mobile phase and the stationary phase. So for example, proline has a relative greater attraction to the stationary phase than it does attraction to the mobile phase than phenylalanine. Hence why proline has spent a greater amount of its time retained on the stationary phase than phenylalanine has. So the reason why amino acids separate is because they have different, so the amino acids have different relative attractions to the mobile phase and stationary phase. So they've got different attractions to the different amino acids have different attraction levels of attraction to the mobile phase and the stationary phase. There's a load of other ways we could word that. That would be good enough. We've mentioned stationary and mobile, and it's the fact that some of them prefer to spend more time retained on the stationary phase than they do attracted or dissolved in the mobile phase. You can talk about solubility as well. Different amino acids have different affinities. Instead of attraction, you can use the word affinity. Name a suitable developing agent. State why the developing agent is needed. Right. So at the end of this, once these different parts of the mixture, these different amino acids have separated out, we're going to want to calculate their RF value. And of course, in order to do that, we need to be able to see them. And one of the problems is amino acids are colorless. And so what we do is we cover the plate with a stain that will show the position of the different amino acids. And the stain we use is ninhydrin, a developing agent, I should say, not a stain. Amino acids are colorless. Ninhydrin will color them purple. So they end up looking purple once you add ninhydrin, and that means we can now go ahead and calculate the RF values. Awesome. And then the final part to this question, 3.7, determine the RF value for TYR. So all you need to do here to determine the RF value for TYR is get your ruler out and measure the distance. So this is your ruler. Measure the distance between the baseline and the solvent front. So first you're going to RF is equal to, you want this distance from the baseline to the solvent front. and that is the distance moved by the solvent. And then you're going to measure the distance between TYR, which is the particular amino acid we're interested in. You're going to measure the baseline to TYR. So you're going to divide the smaller distance by the bigger distance, and that will give you the RF value. And the equation to do that is distance moved by TYR. What a mixture of capitals. Right, yeah. Distance moved by TYR. And then you just want to divide that by the distance moved by the solvent from. Distance moved by solvent. And that gives you the RF value. And your RF value here is going to work out to be 0.54. And you can kind of see that it's just moved over half, just over halfway. You should never get an RF value greater than 1 because your mixture cannot have a greater affinity to the solvent than the solvent does to itself, essentially. And here we go. That's the final mark of that question. So make sure you leave a comment, hit the like. Let's get to the marks. Okay, so what we got here is question 4, and this is a really difficult 6 marker. So a student is given 2 aqueous solutions, L and M, both contain iron salts, so we know they've got Fe in there. The student does a series of tests on the solution, so you can see they've added ammonia solution to both L and M, which are both sorts of iron, so I know FeX, Fey, whatever. They've also added some sodium carbonate solution, which can normally tell you between Fe2 plus and 3 plus. They've added dilute nitric acid, which didn't do anything on its own, but then they added barium chloride, and we got a white precipitate with one and no change with the other. So you've got to know, what does the barium chloride test for? And then the silver nitrate test, what does that test for? Because that made a white precipitate with L, but not with M. And then the question, the answer to the question needs to be broken down into identify all the precipitates formed in these tests. That's going to pick you up some marks. Explain why gas or effervescence was given off with L, but not with M, and then give the ionic equation for all the reactions. So I'm going to start with L and go through all the tests in the column labeled observations with L and try and explain those. This is a very hard question. You know, you might be happy you still come out with an A star if you can walk away with this one with 3 out of 6, because it's a very hard one and you need a lot of revision cards to revise all of these equations and learn all of this stuff to do with your transition metals and your complex ions. So first of all, here we're adding ammonia solution until it's in excess. But the reaction with both of them in excess didn't really do anything. They were both insoluble in excess. I think you'll find the excess ammonia is what you're adding that to find out if you've got copper in there, which we don't have. So we've got ammonia. We add it to iron 3 plus, and what we'll find is that it's quite a good acid with iron 3 plus, so it will donate those hydrogens and we'll get some ammonium ions formed, and you just balance this equation up. Now you might say, how do you know that it's iron 3 plus? Well, Fe3 plus compounds tend to have red brown colors like rust, iron oxide, iron 3 oxide, and those type of things, whereas you get the green colors when you're dealing with iron with the Fe2 plus. So straight away that red brown precipitate makes me think, oh, I'm dealing with Fe3 plus. And what is that red brown precipitate? It's FeOH3 aqueous, or FeH2O3 OH3. It's not aqueous, it's going to be solid because it's a precipitate. Now, I haven't put all the symbols, but I should have put aqueous for some of these and solid brothers, but I'm being uber lazy. So you need this ionic equation, but you won't get the mark for this equation unless you also do the equation for L when it is reacted with sodium carbonate solution. So we're going to do that one now. Now, why did it give off effervescence? Why did it give off carbon dioxide, L, when reacted with sodium carbonate solution? This is because Fe3 plus is smaller than Fe2 plus, which formed the green precipitate with sodium carbonate, but Fe3 plus is smaller than Fe2 plus, so it has a higher charge density, i.e. a greater positive charge spread over the same area or a smaller area. So this means it's more polarizing to that carbonate ion, and it has the ability, therefore, to donate hydrogens more easily. So this is why Fe3 plus is a stronger acid, or has a stronger acid effect. Okay, so the equation for this, which you need to get both equations, one for the ammonia reaction and one for the carbonate reaction, to just score 1 mark for each of them. So you need both reactions for L for 1 mark, both ionic reactions for M. Actually, there's 3 reactions for each. We'll come on to the third one in a sec. So we want to do the same thing here. So FeH2O6,
3 plus, reacts with carbonate ions to form FeH2O3, OH3, plus carbon dioxide, and of course, plus 3 water molecules. And so that is your reaction, your ionic equation. You should really put AQ next to anything that's ionic there. So next to the FeH2O6 3 plus as well, but there we go. And the water obviously is going to be a liquid. And the precipitate is the FeH2O3 OH3. And you get the same precipitate formed with ammonium or with carbonate solution. You get that same red-brown precipitate formed. And the identity of the precipitate is FeH2O3 OH3. Okay. Right, moving on. We've now got the third bit. So we know that L contains the 3 plus ion, and that was identified by its reaction with the carbonate, but also from the red-brown precipitate it forms. Now, it had no change with the nitric acid and no change with barium chloride, which means that's normally the test for sulfate ions. So we're not dealing with iron 3 sulfate, but it does give a white precipitate with silver nitrate. And that means that it must contain chloride ions, because when you do the silver nitrate test and you get the white precipitate, it's normally chloride ions. So we're looking at Ag plus for the ionic equation, plus chloride ions, Cl minus, goes to AgCl with a solid symbol as it's a precipitate. And the Ag plus and the Cl minus are ionic, so they're going to be AQ. But again, writing all those, it's just too long for me at the moment. Right. So the identity of L then, we've identified that it has an Fe3 plus ion, and we've identified that it has chloride ions. So its identity must be FeCl3, and that's a solution. That's aqueous, because it told us at the start the student is looking at 2 solutions, L and M, and they both contain iron salts. So our iron salt is FeCl3. Super duper duper. And that is really everything for L. So now what we're going to do, we're going to zing over and look at the results for M. And they're ever so slightly different for M. The precipitates are slightly different that are formed for M. So let's zip over and check those out now. So for M, what are our observations with M? Well, we need to write out the equations and why it didn't react with carbon dioxide. We kind of already explained that with the Fe2 plus 3 plus thing. So we got same thing at the start. We got Fe H2O6 with a 2 plus sign this time. Now we're adding ammonia. How did I know that this was the one with the 2 plus? Again, it's from the color precipitate, because Fe2 plus ions generally form green precipitates. And we've got the Fe2, and that's generally H2O 4OH2, and they're insoluble in excess ammonia, and we get some ammonium ions formed. There we go. And that is that first equation. Again, anything with a positive or negative charge needs to have AQ next to it. And this is a solid precipitate, so it should have the solid symbol next to it. Again, I can't squeeze it all in here. Right, so that's the identity of the green precipitate, Fe H2O 4OH2. Now let's do the reaction with carbonate solution. So we got CO2 minus with 3, that's the carbonate symbol. And this time it's not acidic enough that we polarize the carbonate enough that we get carbon dioxide. So we actually get FeCO3. And of course the carbonate is 2 minus and the Fe is 2 plus. So they come together in a 1-to-1 ratio, and we get 6 water molecules formed, which are the 6 ligands from the original reactant. Okay, so we got our 2 precipitates here. They're both green. One is FeCO3, one is FeH2O 4OH2. Now the Fe2 plus ion is not polarizing enough to form carbon dioxide, hence why we had no effervescence with observation M with the sodium carbonate solution. Okay, now we want to look at the fact that we did get a result, a white precipitate formed with barium chloride, and of course that is the sulfate ion test. So when you have Ba2 plus ions, they react with SO42 minus sulfate ions to form an insoluble white precipitate of barium sulfate. And so this tells us that what was the iron salt M? Okay, so the iron salt M must have been FeSO4. So we're looking at iron sulfate, and that must have been our original aqueous salt, FeSO4. There we go. That's going to get you the rest of the marks for this one. So quite a difficult question. I reckon if I was in my A-level exam and I peeled off 4 out of 6 on this, I'd be more than happy. But of course, we aim for perfection. We want to get 6 out of 6, and it's just one of those difficult A2 topics that you've got to revise inside and out using revision cards. Let's move on.
Okay, we're looking at this question, which is really on shapes of molecules. Let's get into it. Okay, it's quite a difficult one on shapes of molecules and a bit of an unusual maths question here. So question 5, the molar enthalpy of vaporization, delta H with a little VAP, of a liquid is the enthalpy change when 1 mole of a liquid is converted to vapor at the boiling point of the liquid. Student does an experiment to determine the enthalpy of vaporization for water. The student places a large beaker on a balance. They pour 500 centimeter cubed of water into the beaker. They use a 2.4 kilowatt heater to raise the temperature of the water to 100 degrees. Remember, they said to boiling point. They record the mass of the beaker and hot water. They use the 2.4 kilowatt heater to boil the water for 100 seconds. They record the mass of the beaker and the remaining water. The loss in mass is 103 grams. Calculate the enthalpy of vaporization of the water. 1 kilowatt equals 1 kilojoule per second. And down here, this is a real big clue. Our enthalpy of vaporization is in kilojoules per mole. I always like to look at that because what that tells me is that you need to work out the joules or convert them to kilojoules or work out the kilojoules. And then the mole to the -1 means divide by the moles. So your aim is to look at the units in these maths questions. They tell you what you got to do. Work out joules first, then divide by the number of moles. Okay, so let's see if we can do that. I mean, at first you might look at this and think, is it a Q equals MC delta T? But we haven't been given the specific heat capacity. We haven't been given a change in temperature. We've just been told it boils at 100. They haven't told us the start temperature is 0 or 25. So we can't do delta T. So you can't use Q equals MC delta T for this. And in fact, what they have told us is that 1 kilowatt is equal to 1 kilojoule per second. So we can get bang on that straight away. Let's work it out. So let's get into this. All right, we're looking to work out kilojoules per mole -1, which means kilojoules divided by moles. So let's work out the kilojoules. We've got a 2.4 kilowatt heater. Now, what does it tell us there? 1 kilowatt equals 1 kilojoule per second. So we know we were burning off 2.4 kilojoules per second, right? How long did we do it for? We did it for 100 seconds. So what's the total amount of joules we did? We did 2.4 kilowatts for 100 seconds. So we want to times that by 100 seconds, and that's going to give us 240 kilojoules. Now, the fact that you've got divided by seconds and we're timesing by seconds means we can get rid of the seconds. So we're left with 240 kilojoules. Now all I need to do is divide this by N, which is number of moles, and I'll have my answer. So let's give ourselves a nice little mark for that. Right, the next thing, vaporization of water. Oh, we've got mass, haven't we? Look, we've got a loss in mass. Well, what's being lost? Well, it's just pure water in the beaker. So it's water that's evaporating. So we actually know how much water we used. So we've got mass, we've got MR, and we've got times moles. So I need to do mass divided by the MR. And you should all know the MR of water, just 103 over 18. And that is going to give us our moles. So let's work that out. That's 5 something 5. My maths isn't good enough to work that out without a calculator. 5.72. So recurring. So we've got 5.72 moles of water have been lost, right? So what I want to do is 240 divided by 5.72, and that should give me my answer in kilojoules per mole. But 41.9. Now, how many decimal places do these guys want? It doesn't say. I'm going to go for 2. So I've got 41.941. So I'm just going to leave it as 41.941. 0.94, and that is my kilojoules per mole. So I'm going to get a mark here for working out the moles of water, and then a mark for my final answer. Boom. Right, let's move on, do the next part to the question. I did say this question was about shapes of molecules. Well, it's going to come in here a little bit about shapes of molecules and intermolecular forces, this next bit to the question. So let's zing on to this. Table 2 shows some data about 3 compounds that all contain the same number of electrons. So that is kind of key. And we'll look at that in a second. That's a clue for something later. We've got compounds here. So if I type the names of these, hopefully you know the name CH3, CH2OH. That's going to be ethanol. And then we've got CH3, CH2, NH2. That's going to be ethyl amine. This is like a dimethyl. Yeah, so something like that. Right, let's get into this. So all 3 compounds in table 2 are polar. So these are all polar molecules. Ethanol is the most polar. So they're giving us a clue here. Ethanol's the most polar. Ethylamine is the least polar. So that's that one. Ethanol's most polar, that's least polar. Explain why all 3 molecules are polar. So we're going to get a mark. This is the command word. So this is where you're going to get your marks and how you frame your question. So the command is explain why all 3 molecules are polar. I imagine that's 1 mark. And while ethyl amine is least polar, that's going to be a second out the 4 marks. So while ethyl amine is least polar. In your answer, refer to shapes. So if you say what all the shapes of those molecules are, that's the third one. And the relative negativities of the most electronegative atoms. So talking about electronegativity as well. So these 4 black lines I've made in this last paragraph are the 4 marks we need to hit. So explain why all 3 molecules are polar. So what is it that all 3 molecules have that makes them polar? Well, hopefully you can see, like, if you're ethanol, you've got the electronegative oxygen and the positive carbon and hydrogen. Methylamine, it's got the electronegative nitrogen, and then these hydrogens are going to be left delta positive, and the carbon delta positive. So we can see the electron cloud is being drawn from those bonds around that atom there. And of course, the dimethyl ester has oxygen with carbon on each side, and that is going to be also electronegative there. So the fact is they all have electronegative atoms that are drawing the electrons towards them, and this makes them polar. So all 3 molecules are polar. I don't get a mark for saying that because that was actually in the question. So you might say to yourself, this is a bit of a stupid thing to type. So all 3 molecules are polar. What do we want to say? So I want to say ethanol and CH3O CH3 both contain O, C, and O H bonds. O is more electronegative than C or H, so this makes them polar. Nitrogen is also electronegative, more than C or H, and so ethyl amine is also polar. However, ethylamine contains nitrogen, which is less electronegative than oxygen. So the nitrogen's less electronegative than oxygen. This makes ethylamine the least polar. So essentially, they are all polar molecules because they contain oxygen and nitrogen, which are electronegative. However, ethylamine is the least electronegative because the nitrogen is less electronegative than an oxygen atom. And that's why ethylamine is the least polar. The difference between the electronegativity of nitrogen and carbon and hydrogen is less than the difference in electronegativity between oxygen and carbon and nitrogen. So we've covered like two of the marks here, and we've explained why ethylamine is the least polar. We've explained why all the molecules are polar, but also something else to talk about the polarity is the shapes, because if the molecules were symmetrical, uh, they would not be polar. However, they are all not symmetrical. Now, you might say, why are you saying they're not symmetrical? Just use this word, but you might be in the exam and you might forget this word, asymmetry or asymmetrical. They are all asymmetrical, which means they're not symmetrical molecules. We now lead into discussing their shapes. So, both ethanol and I'm just going to call it CH3O CH3 because I can't bother to name that one. And you should do the same. If you can't work out the name of any of these, just refer to it by how they've shown the structural formula in the table. So both ethanol and CH3O CH3 are bent shaped around the O atom, and ethylamine is not tetrahedral. It's going to be, because nitrogen is, yeah, it's going to be pyramidal. And I can't spell that. Pyramidal. There we go. And ethylamine is pyramidal. It's actually trigonal pyramidal, but yeah. So that also contributes to why they're polar. Now we want to get on. That should have got all the marks. Have we talked about the electronegativities of the atoms? Yeah. So now what I want to do is tick through. Right. Let's hit my green cross ticks. Explain why all three molecules are polar. We've talked about that because they're electronegative, blah, blah, blah. Why is ethylamine the least polar? We've said that here. So ethylamine is also polar. However, ethylamine contains, so it's less electronegative. So we've said why it's the least polar. Have the relative electronegativities. Yes, we've talked about the relative electronegativity. And we've also talked about the shapes. So there we go. Now, just for those of you that are like, well, how did I know the shapes were bent? Well, if you think of ethanol, so ethanol has this shape, CH3, CH2. Then we go to the oxygen, and remember oxygen normally when it's only got two bonds, which it normally has two lone pairs around it. And so that, just like a water molecule, is going to give it the bent shape. And then you're going to get the same thing going on with the CH3O CH3, and it's going to be like this. Okay. And then when you look at ethylamine over here, the ethylamine, you've got the nitrogen with one lone pair. Remember, nitrogen's in group 5 of the periodic table, so it's got three bonded pairs and a lone pair. And when you have that situation going on, you are going to form a pyramid, even though my pyramid looks a little shaky there with, whoa, with that bond there. So what I want to do is make that bond a little straighter-ish, right? So there we go. We got our pyramid. I could color that. Yeah, we could like block that and then do the old line thing there if we want. But you get the idea. That's just to explain those shapes and the molecules, how we came up with those shapes. All right, let's move on. No need for me to have a sniff every 5 seconds. I've got a bit of a cold at the moment, so in all my videos, I'm sniffing away like a lunatic. Okay, last bit, last bit, last bit. So here we go. 5.3, explain the trend in boiling points of the three compounds. Refer to intermolecular forces in all three compounds. Do you remember they said that they have the same amount of electrons? So they don't give a mark for this on the mark scheme, which I find annoying, but same electrons. So same van, oh my gosh, the Waals forces. So that's, I guess they say explain the trend, and this doesn't play a part in the trend because they've all got the same van der Waals forces in all molecules. So they don't give you a mark for that. I thought I'd just explain that's the relevance of the electrons. It should lead you, don't talk about van der Waals forces and the size of them because they've just told you they've all got the same electrons. So they're kind of leading us away from talking about that. But what we do have is both, ethanol and ethylamine have hydrogen bonding. So if you remember, there are three types of bonds that do hydrogen bonding: hydrogen fluoride, hydrogen with bonded to a nitrogen, or hydrogen bonded to an oxygen. So both ethanol and ethylamine have hydrogen bonding. The strongest intermolecular force, and so have higher, boiling points. However, as O is more, remember we said this in the last one, it's more electronegative than N, ethanol has the strongest H bonds, right? So these two have got H bonds, but ethanol has the strongest ones because its H bonds are based on the OH bond. Right, what about the CH3O CH3? This has no hydrogen bonding. And you might say, but it has an O and it has an H. How can it not have hydrogen bonding? The O and the H are not directly bonded, so don't make that mistake. This has no hydrogen bonding. Oh my gosh, I can't even write this properly. This is, it has, oh my days, it has dipole, dipole, permanent dipole, dipole, um, intermolecular forces only. Not temporary, but permanent. So permanent. Temporary dipole-dipole forces, a bit like Van der Waals forces. So there we go. And that explains the 3 marks. So I would say the marks here are for pointing out that ethanol and ethylamine both have H bonding, pointing out that ethanol has the strongest hydrogen bonding, and then saying that CH3, OCH3 only has permanent dipole-dipole intermolecular forces. And I probably should say these are not as strong as H. Just in case I hadn't made that clear, these are not as strong as hydrogen bonding, which explains why they're more easily overcome and hence the lower boiling point. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Okay, welcome to Let's Get to the Marks. Going through a little one on KW. Let's get into it. So question 6, calcium hydroxide is almost insoluble in water, but it reacts with dilute hydrochloric acid. We can see COH2 solid plus 2 coefficient HCl aqueous goes to CaCl2 aqueous plus 2 water molecules in liquid form. A student adds 100 centimeter cubed of 0.1 mole per decimeter cubed hydrochloric acid to 0.600 grams of solid calcium hydroxide. 6.1 for 2 marks. Show by calculation that the calcium hydroxide is in excess. So straight away when going through, as you read this, as I'm working through the exam, I think, what is 100 centimeter cubed? That's a volume. What is 0.1 mole per decimeter? Well, that's a concentration, and that is of HCl. So immediately I'm thinking to myself, well, I'm going to get a mark for doing this calculation, C over V. Don't forget that volume is in decimeters. Chemists, we don't like to use centimeter cubed. So what we're going to do here is we want to do C times V equals N and work out our moles of hydrochloric acid. So straight away, I'm going to do 100 over 1,000. Why am I doing that? Well, I want to convert that into decimeters. So 0.1 times times the concentration. I put those in the wrong order, haven't I? 0.1. So essentially what we're doing is 0.1 times 0.1. We're going to get 0.01 moles of hydrochloric acid. So there's a hydrochloric acid, 0.01 moles. What I want to do is look at the ratio now. It's 1 to 2. So for every mole of hydrochloric acid, I need half a mole of calcium hydroxide. So the ratio is 2 to 1 or 1 to 2, whatever you want to say, hydrochloric acid to calcium hydroxide. So I want to do 0.01 divide it by 2, and that's going to tell me how much calcium hydroxide I would need to completely neutralize that hydrochloric acid. So I'm going to need 0.005 5 moles of calcium hydroxide are needed, needed to react completely. Okay, let's find out how much calcium hydroxide we actually have. We either have 0.005 or we have more, which means it's in excess, or we have less, which means the calcium hydroxide is limiting and the hydrochloric acid is in excess. So it says show by calculation calcium hydroxide is in excess. So I'm imagining we must have more than 0.005. We just need to prove it now. Well, we've been given 0.600 grams. What is that? That's mass. So that's going to mean we need this triangle, which is mass over mR times moles. So what we're going to do here is go 0. Oh my gosh, check out the writing when I don't type. It's disgusting. So that's the mass. We're going to divide that by the mR. Let's work out the mR of calcium hydroxide. Okay, calcium is 40.1. Oxygen is 16. Hydrogen is 1. So there's 17 in the brackets times 2 is 34. 34 plus 40.1, we've got 74.1. Let's smash that in the old calc and do 0.600 divided by 74.1. And we're going to get 000, and you get 809, but we can round that obviously to 10. So we're going to say we have 0.0081 moles of CaOH2. So look, you can prove there, right there. Look, we got more. It's excess. That is bigger than that. So calcium hydroxide is in excess. If you want to know how much it's in excess, you could do the moles of calcium hydroxide you actually have minus how much you actually need for complete reaction. And that is going to give us what? That's going to give us 0.00310. Of course, you could do this in standard form if you want. So that is how much calcium hydroxide is in excess. So yeah, boom. Okay, what would you pick the marks up for here? Well, you're going to pick up the marks for working out the moles of hydrochloric acid. Are you going to pick a mark for doing 0.01 over 2, the ratio? Yeah, you'll pick a mark for saying, look, that's how much calcium hydroxide I need. And actually, this is how much calcium hydroxide we actually have. You don't need to do the minus calculation and show by how much are you in excess of calcium hydroxide. You've got 0.00310 or 3.1 times 10 to the minus 3 extra moles of calcium hydroxide. Coolio. Let's move on to the last part of this question because it's a two-parter, and the second part of this question involves KW. So zinging down to the final part of this question, and it's a fat 5 marker. Lovely bubbly. So what we've got going on here, the final mixture contains a saturated solution of calcium hydroxide at 293 K. At 293 K, so they're just telling us temperature is not a problem. The solubility of calcium hydroxide in this solution is 0.4 grams per decimeter. We can change that into moles per decimeter to get a concentration. KW is 6.8 times 10 to the minus 15, mole 2, DM minus 6. Calculate the pH of the solution. Give your answer to 2 dP. So what we need to know here, you need to know this off by heart. You should know this. If you don't know this, fix up because your exams are coming and you have to know this off by heart. KW is equal to the hydrogen ion concentration times the hydroxide ion concentration. So essentially, they want us to, the command is to calculate the pH. And in order to calculate the pH, remember, I need to do the minus log the hydrogen ion concentration. So we need to minus log the hydrogen ion concentration in our calculator. So we need to find that. So I need to rearrange this. I want to do KW divided by the hydroxide ion concentration. And that is going to give me the hydrogen ion concentration. See if you can work that out. Okay, let's go through the answers. So I need to find out this. We've been given KW, so we don't need to work that out, but I need to work out the hydroxide ion concentration. And I've been given that for calcium hydroxide. So I just want to turn that into mole per dm. So I'm going to do 0.4, bit like the previous question, 0.44. I'm going to do grams over the MR. So I'm going to do that over 74.1. So let's do 0.400 divided by 74.1. And that is going to give me uh, 0.0054. So I've got a concentration of 0.0054 mole dm to the -3, and that is of calcium hydroxide. Here's where a lot of people will mess up. Okay, that is not the hydroxide ion concentration. Remember, calcium hydroxide is going to fully dissociate. And so what we're going to have, look at the ratio of hydroxide ions. It's going to be 2 plus, oh my God, this is so messy. This is like beyond messy. Coefficient 2. I'm going to have a ratio of that 2 to 1 to 2. So I need to times 0.0054. So 0.0054 times 2 to get the hydroxide ion concentration. So let's multiply that by 2. And we're going to get 0.0108. So 0.0108. And that is the moles or mole per decimeter, sorry. That is the conc of the hydroxide ions, right? That is the concentration. That's mole per decimeter. It's getting ever messier and messier when I need to really sort out my tools because I'm just using some crusty old mouse pad on the laptop that's really crap for writing. Excuse my language. Right. So we now know Kw, we now know OH minus. So let's smash in Kw 6.80 times 10 to the -15. We want to divide that by 0.0108. That's some bent line. And let's see what that gives us. So we want to go 6.80 times 10 to the -15 in the old calculator divided by our answer to the previous bit. And we're going to get 6.2985. So I could round that again to 630. Yeah, let's round that to 630 times 10 to the -13. And that is the hydrogen ion concentration. Now we need to pH that. So we're going to go minus log this thing up here. So let's minus log it. So bish bash. Start again. Let's go minus log answer equals. Okay, so once I minus log the answer, I'm going to get 12.20. Yeah, it says to 2 dp, so 12.20, I believe. 0076. Da 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 da. I did a bit of rounding there, but there we go. 12.20, and there you go. So, how many marks was this? 5. Lovely. So I guess you're going to get a mark for rearranging correctly. And you're going to get a mark for working out the moles of the calcium hydroxide. And you're also going to get a mark for realizing that the moles of calcium hydroxide are not equivalent to the hydroxide ions. You've got double the hydroxide ions in 1 mole of calcium hydroxide. So we know the ratio is 1 to 2. So now we get a third mark for working out the moles of calcium hydroxide. We then need to do Kw over the moles of calcium, mole per decimeter, sorry, the concentration of calcium hydroxide, which gives us hydrogen ion concentrations for the 4th mark. And then we need to minus log that round to 2 decimal places and get 12.20. Okay, folks, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Okay, so this is the 2023 AQA A-level chemistry paper, and looking at the multiple, it's the paper 3, so we're looking at the multiple choice section. Now, something that I think a lot of AS kids, if they're just studying the AS, get used to is doing multiple choice questions. But when people move on to do the A-level chemistry, they often neglect their skills at the multiple choice. Now, this is a bad thing because the multiple choice paper, you get 30 marks in paper 3 is multiple choice. And if you leave your multiple choice practice right to the end of the 2 years and you're like, yeah, I don't really do multiple choice because all the testing you do in school is paper 1 and 2. So a lot of the mock exams you do, they won't have anything for paper 3 and they don't have any multiple choice questions, which means that a lot of students are underprepared for the multiple choice. I recommend doing every single AS multiple choice and doing all of the multiple choice questions for the paper threes for the A-level chemistry. And you can find those on like the Physics and Maths Tutor website, or you can find them on the AQA website if you look at the past papers and you just select multiple choice practice. Now you'll get all that multiple choice practice from doing those AS papers because they contain multiple choice questions, and you'll get that for paper 1 and 2 in the AS or paper 3 in the A-level chem. And that's what I recommend you do. Get down and do that because you're going to have 30 multiple choice questions to do this summer in the paper 3 exam. All right, let's get into it. Question 7. Once again, I'll pause the video, grab a scrap bit of paper, write down the answer, and then check it off by unpausing the video and watching the explanation. Which row shows the number of each fundamental particle in 1 Mg 25 Mg2 plus iron? So what does that 25 mean? That means it has a mass of 25. We know from the periodic table magnesium has 12 protons, atomic number 12. So if it has a mass of 25, it must have 12 protons, 13 neutrons. So it's got to be C or D. If it is a 2 plus ion, it has lost 2 electrons, so it can't be D. It's going to have 10 electrons, 2 extra protons, makes plus 2. So we're looking at C as the answer. Bang, easy, that one. And you should all get that right. That one is awesome. Now, let's sing down to the next question. So answer was C there. Right, let's look at question 8. So question 8, what is the relative molecular mass of benzene 1,4-dicarboxylic acid? You're going to need to draw this out because all of these are quite similar. So, you know, it's going to be quite tricky unless we draw it out. So benzene, hopefully, you know, benzene is normally C6H6. So hopefully, you know, that is normally what benzene has. But remember, as this is 1,4-dicarboxylic acid, that means we got a little O there and a little OH there. And we got the same thing going off here. I'm doing it to the side a bit weird because I've kind of screwed this up. There we go. So you want to find the molecular formula or the MR of that once you've written it out. This means that the benzene ring, a hydrogen has been substituted for these carboxylic acid groups. So we're actually looking at C6H4. So C6, 6 times 12 is 72, plus the 4 there. For the hydrogen, we're actually looking at 76, whereas we'd probably be looking at 78 for the benzene ring normally. Okay, now we're looking at the carboxylic acid. We've got 12 plus 32 for the 2 oxygen, plus that, so 45. So we've got 45 for each of these bad boys. So combined together, they make 90. So we're going to do 90 at 76, and that is going to give us 166. And that means the answer is B. Boom. Now let's look at question 9. Question 9, which substance has a significant electron delocalization? So you probably know this from GCSE. We all know that graphite has delocalized electrons. The carbon atoms in graphite have got 3 bonds. They're bonded to 3 other. As they're in group 4, it means there's that spare electron hanging about. That's the delocalization. Obviously, sodium chloride's ionic, iodine's covalent, tetrachloromethane is covalent. So there's no delocalized electrons in those. So that one is another lovely, easy one. Then let's check down to question 10. We've got which reaction has a standard enthalpy change equal to the standard enthalpy of formation for barium chloride? So what are they testing you on here? They're really testing you on, do you know your standard enthalpy of formation for barium chloride? What are your key things? Right, we're looking for 1 mole of a substance. So we want 1 mole and we want formed from constituent elements or whatever in standard states. So I'm really looking for standard states and 1 mole of a substance. If I look at all of these, they all form 1 mole of a substance. So that's no help for me there. But form from their elements in standard states. Is barium a gas? No, barium is a solid metal. Is barium going to be an ion? Is anything an ion in its standard state? No. Barium solid, that looks good. That one there. And again, we've got a barium ion there as a solid. That doesn't exist. So you're looking at C. Barium solid plus chlorine gas makes barium chloride. Beautiful. Okay, let's move on to the next question. Again, once again, pause the video at the start of each of these, have a little go before unpausing and checking the answer. So here we go. This is a Maxwell-Boltzmann distribution for a gaseous reactant. We've got the number of particles up the side on the y-axis and energy on the x-axis. What is represented by the total area under this curve? Is it the total energy of the particles? Is it the activation energy for the reaction? Well, hopefully we know that activation energy is normally represented, like AE is normally represented, or activation energy, by a dotted line there. The total number of reacting particles, the total number of particles present. Obviously, the only particles that can react are these ones after the activation energy. So it's not going to be the total number of reacting particles. It's actually D, the total number of particles present. We're now going to look at 12. So 12, the rate of reaction is greater when a catalyst is used without changing the temperature. So which statement explains why the rate of reaction is greater with a catalyst? So basically, how do catalysts increase the rate of reaction? The collision frequency increases because it has no, well, they don't increase the number of collisions. There's no more particles, there's no more kinetic energy, so that's wrong. The collision frequency increases because there's an increase in the average energy. No, catalysts do not carry energy with them that they give to the particles, and they certainly don't increase the kinetic energy of particles. The proportion of successful collision increases. Ah, that's true, because the catalyzed reaction has a lower activation energy. That sounds pretty good to me. And if we think of our Maxwell-Boltzmann distribution, we just shift that dashed line a little bit to the left, meaning there's a greater number of particles who contain the kinetic energy above the activation energy. The proportional is because there is an increase in no, there's no increase in the energy of the particles. Okay, so it's all about changing the position, increasing the proportion of particles with the energy sufficient to successfully react. Right, let's go to question 13. So 13, we are looking at when hydrogen fluoride is added to water at 298K, this is the equilibrium that's established. HF breaks into H plus F minus. At equilibrium, HF is 7.7 times 10 to the minus 3. And F minus is 2.30 times 10 to the minus 3 mole per decimeter. What is the value of the equilibrium constant in mole per decimeter at 298K? So what we have to know here, the equilibrium constant, that's Kc, isn't it? That is equal to products over reactants. So we're looking at H plus multiplied by F minus and dividing that by HF. So it's always products over reactants for Kc. We've been given F, but check this. If 1 mole of HF breaks down to form F, H plus is going to be equal to F. That's like a strong acid, so it's going to dissociate in equal proportions. So really, we've got 2.30 times 10 to the minus 3 times, I could just square that, right? Times 10 to the minus 3. So I'm multiplying them by themselves and then dividing them by HF, which is 7.70 times 10 to the minus 3. And that's going to give me bada bada bing, bada bada bong, bada bada bash. That's going to give me D. Beautiful. Okay, let's go to the next question. I don't have to scroll down for this one. 14, in which oxide is the named element in its highest oxidation state? So we could make a real mistake here because it's not saying which element has the highest oxidation state. It's saying which is in its highest possible oxidation state. So let's look at chlorine. We always like to say that oxygen is 2 minus. So as there's 2 oxygens, that's a total of minus 4. That means that the chlorine here has to be plus 4. Is that the highest possible oxidation state for chlorine? Well, no, it's got 7 electrons in its outer shell, so it could lose all 7 electrons and become plus 7 in theory. Might not be easy, but it could become plus 7. Then we look at magnesium. Magnesium has 2 electrons in its outer shell, so the maximum oxidation state it can be in is plus 2, and magnesium is in a plus 2 oxidation state here. So it doesn't have the highest oxidation state, but it is the highest oxidation state for that element. So the answer here for 14 is B. Let me just prove why it's not the others. Nitrogen is a group 5 element. Here we've got 2 nitrogens. and 4 oxygens. So we've got -8 from the 4 oxygens. So each nitrogen must be +4. What's the highest oxidation state of nitrogen? Well, it's in group 5. It could lose all 5 electrons to become +5. So that's not the highest oxidation state for nitrogen. Sulfur is in group 6. So it should be +6 is its highest oxidation state. Here it's +4 because we got -4 for the 2 oxygens. So sulfur must be +4, but sulfur potentially could be +6. Okay, I hope that's explained that. That's why magnesium 2+ is the highest possible oxidation state for magnesium. Okay. Hokey cokey. Let's go to question 15. And question 15, what happens when water is vaporized? So what we're talking about here is water going from its liquid state to water going to its gaseous state. And a covalent bond breaks. No, the H2O still is like that. Whether it's a gas or a liquid, water is still like that. This covalent bond is not broken, so that's wrong. Intermolecular forces are overcome. That's absolutely right, isn't it? Those van der Waals forces and those hydrogen bonds have to be broken in order for us to vaporize water. So we know this one is going to be B. The enthalpy of them, oh, we don't even need to look at these two. We know that whenever you change the state of a molecule, you are overcoming intermolecular forces. Beautiful. Let's zing, zing, zang. 16 and we got 17 and they fit on the same page. Which species can behave as a Bronsted-Lowry acid in aqueous? So the answer here is who can possibly give up some hydrogen? And the answer here is hydrogen carbonate. Can still go down to just carbonate ions. It can dissociate and release another hydrogen ion. Let's go down to 17. Which change causes the pH of 10 centimeter cubed of 1 mole per decimeter sodium hydroxide to be halved at 298 K? So what we're looking at here, which change causes the pH of 10 centimeters of 1 mole per decimeter sodium hydroxide to be halved at 298 K, kW. Oh, they've even given us a kW. So what we can do is we can work out the existing pH and then do it all for the others, which is a bit of a pain in the backside, to be honest. So we know that kW, yikesy poos, is equal to H plus. Remember, times OH minus. This is the long way to do it. So don't ask me why I'm doing it the long way. kW is equal to H plus times OH minus. And then what we really want to do is minus log the H plus, and that is going to give us the pH. So let's work out the pH of the original solution and then work it out with the changes and see if it is see if the pH gets halved, okay, for each of these, and then we can find out which one it gets halved for. You might want to pause the video and have a go. Okay, so in order to find H plus, I need to do kW over OH minus concentration, and that's going to give me the H plus. So we're going to do that first of all for the original. So we got 10 centimeters of 0.1 mole, sorry, 10 centimeters of 1 mole per decimeter NaOH. So that's going to break down to form 1 mole of OH minus. So essentially, I just want to do kW over 1, and that is going to give me the, so I want to go 1 times 10 to the minus 14, divide that by 1, and I'm going to get 1 times 10 to the minus 14. That's the hydrogen ion concentration. And then if I inverse log that, if I go minus log that, I'm going to get pH 14. So this 10 centimeter cubed has a pH of 14. So which one is going to end up with a pH of 7? Which one of these is going to get a pH of 7? If we add 10 centimeter cubed of water, no, adding that. So adding 10 centimeter cubed of 1 mole decimeter hydrochloric acid, look, that is going to neutralize that to form pH 7. So yeah, that is going to be the answer. That is going to perfectly neutralize that because HCl
plus NaOH. They're of identical concentration, so I have identical moles of each. They are going to perfectly neutralize. Look, that's going to form sodium chloride. So I don't even need, I was going to do all the calculations. There's no need now. We know that the moles of this are equivalent. It's a 1-to-1 reaction. So we're only going to end up with sodium chloride and water, and that if you have salt and water, you have pH 7. If you have no excess acid or alkali, and that is going to be the exact same amount of moles. So I could have just worked out my moles of sodium hydroxide is going to be 0.01 times 1 equals, so I've got 0.01 moles of sodium hydroxide, and I've got the exact same thing going on for the hydrochloric acid because we've got 0.01 decimeters times 1 mole. I've longed this out, but is 0.01 mole. So they are completely neutralizing each other. There's no excess acid or alkali. So we're going to end up with a pH of 7. So that's the shorthand way of working that out rather than having to do all the bloody calculations. Okay, question 18. We got 0.1 mole per decimeter solution of a weak acid with a pH of 2.50. What is the value of Ka for this acid in mole per decimeters? And it's worth 1 mark. All right. Let's see if you can do that. Pause the video, have a go and all that. Right, I'm going to go through the answer and explain how we get there. So we want the Ka. So what we have to remember is that Ka is equal, and you should know this off by heart. If you don't know this off by heart, give yourself a slap on the wrist. Right, maybe not that hard. Ow. So is equal to H plus ion squared over the concentration of the acid. So concentration of the H plus ion squared over the concentration of the acid. So it's straightforward. We just want to do that calculation. We've been given the pH, so you've got to remember, how do you actually go from pH to the H plus ions? So on your calculator, depending on what mode it's in, you should just press Shift Log. And what you're going to get when you press Shift Log on your calculator, you'll get this little box appear like that. And then into that, you want to put minus the pH, so 2.50, and that will give you the hydrogen ion concentration. So smash that in the calculator, and you're going to get 3.16 times 10 to the minus 3. And look, they're trying to catch you out because that's one of the answers there. But all you've done is work out the hydrogen ion concentration. So you now need to divide that by the concentration of the acid. Now, the concentration of the weak acid, HA, is 0.1. So we want to go 3.16 times 10 to the minus 3. Oh, we need to square that. I nearly forgot about that. So square that. And if you square that, you got like 1 over whatever that is, 100,000. Now divide that by 0.1, and you're going to get 1 times 10 to the minus 4. So our Ka is 1 times 10 to the minus 4. And there we go. Boom. Sorry, my dog's barking in the background. Got a little chihuahua that's a little barky. My daughters have got their friends over, so dog's getting excited. Question 19, which statement is not correct about the period 3 elements sodium to chlorine? So remember what sodium is. Sodium's a metal, chlorine's a gas. They're in period 3, the third row of the periodic table. You've got a periodic table in your exam, so do feel free to use it. Sodium has the largest atomic radius. So as we go down a group, generally atomic radius increases. So we go from lithium in group 1 to sodium to potassium. Generally, they get bigger. As you go across the period, they don't really get bigger because you're adding electrons to the same energy level, and yet the number of protons, the nuclear charge is increasing. So if anything, the atomic radius shrinks as we go across the period. So sodium has the largest atomic radius. That might be true, but actually we are adding extra electrons. Let's just see. Sodium has the lowest melting point. It's asking which one is not correct. So we know that sodium probably does have the largest atomic radius. Which one is not correct? Sodium has the lowest melting point. Well, that's definitely not true. Chlorine, right, is a gas, and sodium, right, is a solid. So which one must have the lower melting point? It must be chlorine. So we know this is incorrect. You kind of know the rest of these are correct. Silicon, the highest melting point. Chlorine has the highest first ionization energy. Okay, well, we already know sodium doesn't have a lower melting point than chlorine, so we know that one is incorrect.
All right, let's move on. Let's move on. Let's move on. 20. Okay. Like I say, there's tons of these in paper three. Equal volumes of pairs of solutions are mixed. Which pair forms a buffer solution? So you have to ask yourself straight away with this question, and you've got these different combinations, to which one can form a buffer. What is a buffer made of? Well, you've got like acidic buffers. So normally we go weak acid and a salt of that acid. So typically, oh my God, I can't spell acid. How did that come out as cade? Um, so normally we have a weak acid and a salt of the acid. So you're talking about like ethanoic acid, which is a weak acid. And then something like sodium ethanoate or potassium ethanoate would be the salt of the weak acid. But we can also make a basic buffer. So it could be a weak base and a salt of the base would also be, if we want to make a basic buffer, could also be the situation. So let's check this out. We've got ammonia and ammonium chloride. Now that will cover the weak base and a salt of the weak base. So I'm immediately thinking A sounds like it's a buffer because we got a base, NH3, and then we got ammonium chloride, right? Which is a salt. NH4Cl is a salt of that base. Ammonia and methylamine, no. It's just two bases there. Ethanoic acid and methanoic acid, no. It's two weak acids. There's no salt there. Hydrochloric acid and sodium hydroxide, you're looking at a strong acid and a strong base. You need a salt and the acid, or an acid and the salt of the acid, or a base and the salt of the base. The only one that covers that is A. Okay, let's zing to question 20. 21. Barium metal is added to a large excess of water. Which observation is correct and complete? So if you're going to add a metal, and it's a reasonably reactive metal, to a large excess of water, we're going to definitely get effervescence. That, of course, folks, is the hydrogen gas. If you're using alkaline earth metals or alkali metals, you're going to get hydrogen gas released, right? And you're going to get a hydroxide formed. So we're going to get barium hydroxide and hydrogen gas. So the colorless solution, group 1 and 2 metals always form a colorless compound when dissolved, like in aqueous solutions. So like barium hydroxide is going to be colorless, and you're going to get hydrogen gas produced. So B is the correct answer. Group 1, 2, and 3 metals form white solids or colorless solutions. It's only your transition metals that give us those colored compounds and colored solutions. Which species is the strongest reducing agent? So again, this is really highlighting, what does reducing agent mean? A reducing agent causes substances to get electrons, right? Reduction is gain of electrons. So oil rig, they're going to gain electrons. Itself is oxidized. So what I mean by that is the reducing agent must lose electrons. So I'm asking myself, who here is the most capable of losing electrons? Fluorine, covalently bonded, doesn't want to lose an electron. Iodine, same thing, probably more susceptible to losing an electron than fluorine. Fluoride ions, um, does it want to give away that electron? No. Iodine is larger. That outer electron is further from the positive charge of the nucleus, and it has more shielding. So iodide ions, not iodine, iodide ions are going to be the strongest reducing agent. And that's shown. You should know all those reactions that show that as well. They'll sometimes test you on that, the reactions. So 23, which statement about the shapes of ions is not correct? So CoCl4, so CoCl4 2 minus is square planar. That doesn't sound correct, does it? Because we're going to be looking, oh my gosh, this is like the worst drawing ever. It's going to be tetrahedral. Yeah, tetrahedral. So straight away, that is not square planar. So that is not correct. Crazy bloody dog barking in the background's doing my head in. I might have to strangle the chihuahua in a minute. 24, which compound can decolorize acidified potassium manganate solution? So what we have to look at here is that our manganese ions are 7 plus
in this solution, and they like to go to Mn2 plus when they go colorless. So when they're colorless, they go to Mn2 plus. Okay, where was I? Sorry, I had to stop there. The Chihuahua going mental. Right, Mn7 plus. So that's kind of like purple in solution, right? And when it goes to Mn2 plus, it goes colorless. So what we're looking at here is what's happened to the oxidation state. It's gone from 7 plus to 2 plus, which means it's gained electrons. Which one of these bad boys can afford to give away electrons? Well, if we look at Ag, can Ag become 2 plus 3 plus? No, it's not that one. Copper's already in its 2 plus state. That's its highest oxidation state. We don't get copper 3 plus 4 plus, so it's not that one. Then we've got iron here. What state is this in? Well, sulfate ions are that's going to be 2 plus, right? Because sulfate ions are 2 minus. So, and then we look here, the sulfate ions are 2 minus, and we got 3 of them, so -6, and we've got 2 of those. So here, iron's in a 3 plus state. So iron actually in this 3 plus state cannot give away any electrons. It's already given away its maximum amount of electrons, so it can't help out here. But of course, the iron 2 plus in iron sulfate has room to give away another electron, add it to the Mn7 plus, and bring it down to the Mn2 plus. Obviously not in a 1-to-1 ratio, but that is the only one that can still give away some electrons and reduce this potassium manganate 7. Boom. Right. Lovely jubbly. Okay, moving on. 25. Oh my good gosh, 26 is looking ugly, peeps. Look at that. Right, 25. Which statement about catalysts using reactions at equilibrium at constant temperature is correct? They are which statement about catalysts using reactions at equilibrium? They are always in a solid state. Well, I don't know about that. They increase the rate of the forward reaction, but decrease. No, they don't do that. That would interrupt the equilibrium. They have no effect on the value of the equilibrium constant. They make the forward reaction more exothermic. No, these are all garbage. The answer here is C. As you should know, catalysts do not affect the position of equilibrium, and so therefore do not affect the equilibrium constant. The only thing catalysts do to do with equilibrium is they make you reach the position of equilibrium faster. So they bring you to equilibrium faster, but they do not change the position of the equilibrium. Therefore, they do not affect the equilibrium constant. Right, let's get down to this ugly reaction scheme down here. So if we check out this reaction schemanos, so for 26, we've got step 1, that's a dimethyl ether, and then we got and then alkyl nitrile, and then double bond. Okay, carboxylic acid group, bada bada bing, bada bang. Okay, but oh right, what the hell's the question? Which step is shown with a correct reagent and correct condition? So step 1, hydrogen cyanide dissolved in water. Step 2, potassium hydroxide dissolved in warm water. No. Step 4 is methanol with an alkaline catalyst. So is methanol going to turn that with an alkaline catalyst? Step 5, hydrogen with a nickel catalyst. So I'm just giving these a brief. Hold on, double bond, single bond. Right, look here. Of course, this is hydrogenation. Hydrogen with a nickel catalyst is definitely capable of turning that double bond into a single bond in hydrogenation. We could also use tin with hydrochloric acid, I'm sure. But we go for hydrogen with a nickel catalyst. That is definitely a correct reagent and condition for hydrogenation of the double bond. Okay. Zing, zing, zing. Which process does not involve a heterogeneous catalyst? So straight away, you've got to know, what does heterogeneous mean? Heterogeneous means that the catalyst is in a different state to the reactants. So catalytic cracking of alkanes, the alkanes are vaporized, right? We vaporize the alkanes and we pass them over sort of solid alumina or silica. And so they definitely are heterogeneous because we pass the vaporized alkane over them. The contact process, what's that? Vanadium pentaoxide and sulfur trioxide or sulfur dioxide. So they're heterogeneous. They're in different states because the sulfur dioxide's a gas. Decomposition of ozone. Um, well, ozone is a gas, isn't it? O3. And the chlorine-free radicals are gas. So they are a homogeneous catalyst. So they are in the same state, which is both are gaseous. And then we've got the Haber process, which involves solid iron. And we have hydrogen, which is gaseous, don't we? And nitrogen, which is gaseous. So yeah. That is heterogeneous because our catalyst is in a different state to the reactants. So it's definitely C, which is the decomposition of ozone, because you've got chlorine and you've got ozone. So, and they're both in a gaseous state. So that's homogeneous. Oh, we're nearly there, folks. 28. The equation for the complete combustion of butane is C4H10, 6.502 goes to 4CO2 plus 5 water molecules. What is the mole fraction of butane in a mixture of butane and oxygen with the minimum amount of oxygen needed for a complete combustion?
So, well, we can see the minimum amount of oxygen needed is given to us right here. It's 6.5 to 1. So we've got 6.5 to 1 is the ratio of oxygen to that. But they want the mole fraction. And what is the mole fraction? The mole fraction is the amount of moles of one of the reactants over the total, or the amount of moles of the substance in the mixture over the total. So we want 1 over 7.5 because we've got 1 mole of butane and 6.5 of oxygen. So the mole fraction of butane within the reaction mixture, in a mixture of butane and oxygen, is going to be with the minimum amount of oxygen needed for combustion. What is the mole fraction of the butane? It's going to be 1 over 7.5. So I need to smash that in my calculator because I can't do that in my head. Double divide divided by 7.5 equals 0.133, and that's recurring. It's going to be A. So hopefully you get that. We've got 1 mole of butane, 6.5 moles of oxygen. What's the mole fraction of the butane in a mixture of butane and oxygen, which is all of this, where we have the minimum amount of oxygen, which is 6.5 for complete combustion. So the total moles of gas are 7.5, and the amount of butane within the 7.5 is 1. So 1 over 7.5. Enough, Tom, enough. Move on, buddy. Right. I need to shrink this so we get all of that in. Bosch, which is not a possible product of a reaction between potassium hydroxide and this. I've seen this kind of question quite a lot, actually. That straight away, boom, you ain't gonna get that. If you can get that, then you can get that. This is just adding a double bond either here or here. So if you can get one of them, you can get the other one. So the fact that they're both there means we have to be able to do that. That is just nucleophilic substitution, OH attacking there and joining on there. And here, there's no way we can turn that into a carbonyl group. So this is not a possible product with just KOH. That ain't going to happen. Right. Trying to zing through as quick as I can. Time is of the essence. 30. Most scientists believe the concentration of ozone in the upper atmosphere should not be allowed to decrease. So they want to maintain our lovely ozone in the atmosphere. They don't think we should decrease it. Which statement is the reason why they think we shouldn't decrease ozone in the atmosphere? Ozone helps to prevent global warming. That's not why they want it in the atmosphere. Ozone is efficient. It is a good disinfectant. It kills bacteria and it kills viruses, but that's not why we want to have lots of it in the atmosphere. We're not under threat from massive comets delivering dangerous viruses and bacteria, at least as far as I know, we're not, through our atmosphere. Ozone helps to remove pollutants such as chloroalkanes. Well, yeah, that's not really a benefit. Ozone absorbs ultraviolet radiation. That's the exact reason we don't want to all be getting sunburn. If we deplete that ozone in the atmosphere, we're all going to fry, and the number of skin cancer cases are going to go through the roof. Okay, we are up to question 31. So compound X can be converted into an alcohol in a two-stage process using concentrated sulfuric acid, forms an intermediate, and then we use excess water to make an alcohol. What is the name of compound X? Okay, so what we're going on here is compound X is going to be propene. It's going to have that double bond. What happens is this will join to form like propyl hydrogen sulfate, something like that. It forms that intermediate. So the concentrated sulfuric acid. Then you add the excess water, and it forms an alcohol. So that is in your section of your content. If you're wondering, oh, how come I don't know this reaction? It's probably one of the more difficult AS ones. It's a year 12 reaction, and it comes under the content in your revision guide or your books under alkenes. So you want to look that up. If you don't know it and you haven't been able to spot this, you want to check that out. It's quite a complex mechanism where the sulfuric acid joins to the alkene and you get an intermediate. In this case, it's like, oh gosh, propyl hydrogen sulfate. And then because it's propene, if it was ethene, it'd be like ethyl hydrogen sulfate. And then what you want to do is you add excess warmed, I believe, water molecules or water, and it goes to alcohol. So if you don't know that one, get revising because that is a hole in your content. Right, 32. Which is a correct equation for the oxidation of 1-phenylethanol? O represents oxygen from an oxidizing agent. So which one of these is the correct equation for the oxidation of 1-phenylethanol? So 1-phenylethanol, what the hell does that mean? Well, that means we have a benzene ring and then we have ethanol attached. And we want to oxidize that. Let's see. So 1-phenylethanol C6H5, CHOH, CH3. Yeah, it could be that. Could be that. Yeah, actually, let's zing that around the other way. And then it is going to form. Oh, yeah, it's going to form a. Yep. So it's going to be D. So it's going to be like CHOH, CH3. And that's the ethanol attached. So it's going to form that there. Here, it can't form this because this has rearranged. This has rearranged that to form an aldehyde, and it can't form that. So it's going to form a ketone there. That's the correct answer. Right. Okay. Let's zing. 33, the skeletal formula of two compounds are shown. So what have we got here? We've got one, two, three, four. What's that? Butanal. And then we've got one, two, three. What's that? Two methopropanol. Which method would distinguish between samples of these compounds, comparing fingerprint regions of their infrared spectra? Okay, obtaining molecular masses from their high resolution. Well, their molecular mass is the same, right? So MR. Of that has got to be equal to that because they have the same amount of carbon atoms and oxygen atoms, so we can't use that. Warming with acidified potassium dichromate. Well, they're both aldehydes, they're both going to decolorize that. Oh no, they're both going to go green to orange or whatever, orange to green. They're going to change. There's going to be a color change with that for both of them. There's no difference there because that one has a methyl group. Warming with Tollens reagent, again, they're both going to form a silver mirror. So that is not going to help us. So I guess we're going to have to compare that unique region called the fingerprint region on infrared spectra that will be unique depending on the bonds for that particular substance. And each substance on the Earth has its own unique fingerprint region. They're going to have the same region for the carbonyl bond. That's not going to be different, but they're going to have a unique fingerprint region because they're different molecules. So you can always use that to identify something. Okay, zing, zang, zong. What are we on? 34. Nearly there, folks. Which compound is the strongest base? So which of these compounds is the strongest base? What does a base want to do? That's what we have to ask ourselves. What does a base want to do? So a base wants to accept protons slash hydrogen ions. So which one of these is going to be most likely to accept protons or hydrogen? I don't know what that is. That's supposed to be hydrogen ions. So which one of these is more likely to do that? Okay, so what are we doing here? We're looking at which one of these is the strongest base. So bases want to accept protons. So it's all about which of these has the most available pair of lone, you know what I mean, electrons on the N atom. So on which of these is the electrons most available? Well, this one is the least because the benzene ring is electron withdrawing and it draws the electrons into the ring. Ammonia, ammonia is kind of in the middle because the electron pair is available, but it's not being pushed forward anymore. This is not a base at all. So that is not a base at all. All these three are bases. Now, this is an aliphatic, not aromatic. So it's not a benzene ring. So it's not electron withdrawing. It's actually supposedly electron donating. And so makes the nitrogen here, it makes its pair of electrons more available to accept that base. And so that amines with an aliphatic group, i.e., it could be a cycloalkene kind of group there, or it could just be propyl, ethyl, methyl, whatever. They are electron donating. So they are going to actually further increase the availability of the lone pair of electrons on the nitrogen. So that has got more basic properties. This is the weakest type of base when you have a benzene ring, a phenylamine essentially, because the electrons are withdrawn into the delocalized ring. And then ammonia has come bang smack in the middle. So this is the strongest base, followed by ammonia, then this one in third, and then this is D is not a base at all. So the answer here is A. Um, Only two more questions to go. Let's smash these out. Which statement about enzymes is not correct? The tertiary structure of an enzyme influences which molecules combine to the active site. That is correct. So that's not correct. Obviously, their tertiary structure, their three-dimensional shape is important as to what things can fit in, like a lock and key. The action of enzymes can be inhibited by a molecule or ion that binds to the active site. That's absolutely true. So we're looking for the not correct. Enzymes work equally well on both optical isomers of a substrate. No, that's not true. Computers can be used to design drugs to block active sites on enzymes. That is true. Yeah, so no, most enzymes are not going to work very well on both optical isomers because in enantiomers, they are not, they're mirror images of each other. But remember, chiral, they're like your left hand and your right hand. They're not the exact, your left and right hand are not the same shape, so will not fit in the same glove, essentially, as well. So yes, optical isomers, the two different versions of an optical isomer will not bind equally well to an active site. Okay, enough waffle whiffle. It's the last question. Ba-ba! Oh, cisplatin. Cisplatin has the formula PTNH32Cl2. Cisplatin is an anti-cancer drug that prevents replication of DNA. When cisplatin bonds to DNA, which is the correct ligand replacement reaction, a replacement of one NH3 ligand, a replacement of two NH3 ligands, replacement of one NH3 ligand and one Cl minus ligand, or the replacement of the two chloride ligands. It's the two chloride ligands that are replaced. And if you don't know that, I suggest you make a little revision card on cisplatin and learn that up. It's one of those specific things that will separate the superstars from the stars. So You want to be a superstar, an A-star student, you need to know your little details like that about cisplatin. Okay, guys, I hope you found that helpful. Don't forget, sharing's caring. Hit the like, punch the bell, subscribe. Let's get to the marks.
You're still here? It's over.